Okay, we're moving on to step 3 of analyzing the function. Again, we're going to find intervals of concave up, concave down, and inflection points. I just wanted to step back again, remind yourself what the original function was because it is on the previous page. It was negative x cubed plus 3x squared plus 9x minus 27. I also wanted to remind you we already found that derivative being negative 3x squared plus 6x plus 9. That was the non-factored version, which is fine because that's what I want to use to find the second derivative. So part C again says determine the intervals of concave up, concave down, and find the inflection points. So the way I'm going to do that is I'm going to analyze the second derivative. Well, the second derivative, we need to look at the derivative of the first derivative. So the derivative of the first derivative of negative 3x squared would be negative 3 times 2x, which is a negative 6x. The derivative of 6x would be 6 times 1, which is just 6, and the derivative of 9 is 0. So the derivative of negative 3x squared plus 6x plus 9 is negative 6x plus 6. Again, I need to set this equal to 0 or undefined. It's never undefined because it's a polynomial, so I set it equal to 0. Subtract 6 from both sides, I'd have negative 6x equals negative 6. Divide both sides by negative 6, and I'd have x equals a positive 1. Again, this is a possible inflection point. This is not a critical number or critical value. This is a possible inflection point. The only way we know it's an inflection point or not is we go ahead and we look at that number line. So here's x equals 1. We know our second derivative is equal to 0 when x equals 1. Okay, so the idea is what is it in the first interval? Well, that's negative infinity to 1. And what is it in the second interval? That's 1 to infinity. What are we going to do? Let's do the sign chart. So we have our x values, and again, since we're analyzing the second derivative, we plug it into the second derivative. I'm just going to go ahead and use negative 6x plus 6. You could factor it if you prefer, factoring out a negative 6, but I don't care about that. It's so easy to plug in numbers here. We need any number less than 1, so how about the number 0? And we need any number bigger than 1, so how about the number, I don't care, 10? So what would we have the sign if we plugged in 0? Well, negative 6 times 0 is 0 plus 6 is positive. So when I plugged in a 0, I got positive. That means anything in that interval must be positive. Let's try 10. Negative 6 times 10 is negative 60. Plus 6 would be a negative number. Since that test point was negative, every point in that interval must be negative. So why do we care about that? Because if we know the sign of the second derivative, we know information about our original function. Any place the second derivative is positive, I know my function must be concave up. Any place my second derivative is negative, I know that my function must be concave down. And then again, because my domain is negative infinity to infinity, and at x equals 1, I change concavity, I know when x equals 1, I have an inflection point. So the inflection point occurs when x equals 1, but we have one more thing we need to do. We actually need to find the value of that inflection point. So how do I do that? I have to plug it in back into the original function, which again was negative x cubed plus 3x squared plus 9x minus 27, and I'm going to plug in the value 1 here. So I already had this typed into my table feature, so it's really nice. I just had to turn my calculator back on, plug in the number 1, and I got a number negative 16. So that tells me the point 1, negative 16, is an inflection point. Okay. So where is it concave up? Again, it's concave up anytime the second derivative was positive. That was the interval negative infinity to 1. Where is this function concave down? That's any place that the second derivative was negative. That is from the interval 1 to infinity. Inflection points, an inflection point is the point where it changes concavity. That was at the point 1, negative 16. Okay. So with all of that, now that I've analyzed the original function, I've analyzed the derivative, and I've analyzed the second derivative of the function, I'm able to put all of this information together and graph it on a single graph. When you graph this, I am not so concerned about the accuracy of the graph, meaning, look, the scale of it might be completely off, and the x scale and the y scale might be completely different. What I am looking for is not an exact replica of the graph to scale. What I'm looking at is the exact shape of the graph with the important points labeled. What are the important points labeled? The x and y intercepts from step 1, the maxes and mins from step 2, the inflection points from step 3, and then I'm looking at the shape between all of those graphs. So how do we do this? Well, what I really like to do is I like to step back and I like to look at a few things. I take step 1, step 2, and step 3. Again, step 1, the information from the original function. Step 2, the information from the derivative. And step 3, the information from the second derivative. And I like to put them all on the same graph. So for instance, the first thing that I noticed is that there was x-intercepts at -3, 0. So here's plotting a point -3, 0, and also at 3, 0. I noticed that I had a y-intercept, and I'm just going to put a dot down here because, again, the y scale doesn't matter. I remember that I had a y-intercept of 0, -27. So I'll plot that point right there. Okay, so that's my information that I got from the original function, step 1. Now let's look at the information we got from step 2. From step 2, I realized I had a minimum at the point -1, -32, so I'll plot a little point right there, -1, -32, and I'm just going to write minimum right here. And then I also realized that I had a maximum at the point 3, 0, so I know that point is a maximum. Great. And then what I also want to do is I want to take that number line that I got from step 2. So if you look in step 2, think about where did we break up the number line on step 2. And what I'm going to do is I'm going to draw the exact number line from step 2 below this graph. What I have when I did this, what I had was a graph that I broke up at -1 and at 3. I'm going to come down here and I'm going to draw this below it. Here's x equals -1 and x equals 3. And then what I want to do is I want to think about the sign of the derivative on each one of those. So the sign of the derivative was negative for the first, positive for the second, negative for the third. And again, at x equals -1, I know I have a minimum, and at x equals 3, I know I have a maximum. Okay? So that's all my information from the first derivative. Now what I want to do is do the exact same thing with the second derivative. With the second derivative, I know I have an inflection point at 1, -16. So I'm just going to sketch roughly where it would be. Again, my y scale is not going to be exact here, and I don't really care about that. This is 1, -16, and I know that this is a inflection point. Okay? I want to do the same thing as I did with the number line that I created with the first derivative. You see how I drew that below this graph. I'm going to do the exact same thing with the number line from the second derivative. I'm going to draw this exact number line below it on the graph. So I break it up at x equals 1. And I know that's an inflection point. I consider my second derivative on those intervals. So my second derivative everywhere before 1 was positive. So it was positive in each one of these cases. And everywhere after 1 it is negative. And why do I care about that? Because when I put those two things together, that can tell me the shape of the original function. Again, let's see how we can do this. What is the second derivative? The second derivative is positive, so that means I have to be a smiley face, right? Concave up, smiley face. But then my first derivative is negative, so I have to be decreasing of a smiley face. So what part of a smiley face is decreasing? That would be the left part of a smiley face. So the shape of my graph on the interval -∞ to -1 must be the shape of the left half of a smiley face. Let's look at the next interval. The next interval, my second derivative is positive. Again, I'm a smiley face, concave up. But now my first derivative is positive, so that means I need to be increasing. So which half of a smiley face is increasing? It's just the right half of the smiley face. So in the interval -1 to 1, I have to be the shape of the right half of a smiley face. Let's look at the next interval from 1 to 3. From 1 to 3, my second derivative is negative, concave down, which is a frown, so I know I'm a frown. My first derivative is positive, so I need to be increasing. So which part of a frown is increasing? It would be the left part of a frown is increasing. So my graph has to be the shape of a left part of a frown. Let's go to the last one. My second derivative is negative. Again, second derivative negative means concave down, which is a frown. My first derivative is negative, so that means I have to be decreasing. So which half of a frown is decreasing? It's the right half of a frown is decreasing. So the shape of my graph has to look like the right half of a frown. Okay, so what have I done? I have labeled every single point on the graph from steps 1, 2, and 3. I've used the sign chart, the number line from the first derivative and the number line from the second derivative lapped on top of each other to determine the exact shape of the graph in the intervals. Now what do? I play a game of connect the dots using the proper shape. So I have to connect the points -3, 0 and -132 using the left half of a smiley. So I'm going to do it. It's going to look something like that right there. Now I look at the next interval from -1 to 1, so I have to go connect the points -1, -32, 0, 27, and 1, -16. All three of those points I have to connect using the right half of a smiley, so do it. Now I go from x equals 1 to x equals 3. I have to connect the point 1, -16 and the point 3, 0 using the left half of a frown, so do it. And then to the right of x equals 3, I have to go from the point 3, 0 and go down using the right half of a frown, so do it. And now what we have done is we've created the exact graph of this function. Again, the y and x aren't to great scale, but we know every single important point on this graph and the exact shape of this graph on every single interval, and we didn't use one bit of technology to do this whatsoever. That's absolutely amazing. We could sketch this graph extremely accurately using absolutely no technology, finding all that important information. So now and only now is the point in time where I would actually go into the computer, go to desmos.com, type in the original function. You're going to have to adjust your window to see it, but you're going to see we got the exact shape of the graph, every single important point of the graph exactly dead on. Really, really cool process, a long process, I agree, but an important process because remember, they didn't used to have graphing utilities. They didn't used to have things like Desmos, so they had to do this by hand, and using calculus gave them a great way to look at functions by hand without having to graph an infinite amount of points, essentially.